Today I'm going to talk about some convergence properties of RL algorithms. Specifically, I'm going to show my understanding of these algorithms, like the behavior of these algorithms using a graphic way. So for value-based reinforcement learning algorithms, everything starts here, dynamic programming. So in dynamic programming, we do the full backup. So actually, we need a model, and then we can do the full backup. And then we do synchronous value updates or policy updates on the all state space. And similarly, we can do asynchronous dynamic programming, where we still do full backup, but we only update one state every iteration of the algorithm. And TD learning is a class of methods which is similar to ADP, but now you don't need the model. While you can just do a sample backup, and basically you can still do asynchronous kind of learning. So it's very interesting that TD learning, the convergence of TD learning. For every TD learning algorithm, you can find its counterpart in dynamic programming or asynchronous dynamic programming. And the convergence property of the TD learning method is highly related to its counterpart in DP or ADP. So what is the scope of today's talk? So the first one means the problem setting of today's talk. So under what condition do we talk about convergence? So discounted expected total bounded reward, this is the most strict setting, however, in this setting we have the strongest theory guarantee. And today I'm going to talk about tabular single-step DP or ADP methods. And because, as I mentioned before, understanding these two class of methods is really important for us to understand simulation-based methods. So let's start. Let's get started. So consider an MDP where it only has two states, S1 and S2. And here I draw a space of the value function. A space of the value of these two states. So it's a 2D space, and every value should be a point in this space. And just remind you guys of the Bellman operator is a contraction mapping. What is Bellman operator? So there are two kinds of Bellman operators. One is the Bellman optimality operator, and the other one is the Bellman operator for policy pi. And when we talk about contraction mapping, there are two different kinds of norms. So norms are basically the distance in the space, in vector space. So there are two kinds of norms, d pi norm and max norm. So we know that both Bellman operator for policy pi and Bellman optimality operator are contraction mapping under the max norm. And in addition, Bellman operator for policy pi is also a contraction under the d pi norm. Okay, let's start from the simplest case policy evaluation. So I just copy the contraction mapping equation in that place. And so I'm going to show its meaning in a graphic way. So let's start from V0, which is your initial value estimates. And suppose the the true value for policy pi is in this green dot. And so we're going to interpret the V0 minus V pi under the max norm. So this part, what does this part mean? Because max norm is actually the maximum elements, a maximum of all absolute value of elements of the vector. So in this case, it's actually the maximum over this line segment and this line segment. And obviously that this one is longer than this one. So V0 minus V pi under the max norm is going to be the magnitude of this line segment. And we multiply these by gamma, which basically gives you like this part. And now you see that as long as you apply a Bellman operator t pi to v0, then it's going to be inside of this square. And we apply the Bellman operator and find the v1. And we just keep doing the same thing. And now the vertical line segment is going to be is actually a longer line segment. And we find the second square, which says that t pi square v0 is going to lie inside of this area. And we just keep doing the same thing again and again. What you observe here is that every time you draw this square, the size of the square shrinks. And this is because we have this kind of gamma, which is smaller than 1. So eventually it's going to converge. It's going to converge to this v pi. If you apply the Bellman operator t pi many times, infinite times. Okay. And now let's think about the value iteration. Value iteration is actually very similar to policy evaluation because in value iteration you have Bellman operator t. Well, in policy evaluation you have Bellman operator t pi. But both these two Bellman operators, they are contraction mapping under the max norm. So everything looks similar as policy evaluation. Okay. So now let's think about asynchronous policy evaluation. Things becomes more interesting. Well, in asynchronous policy evaluation, you don't update all states values. Instead, you only update one every iteration in your algorithm. So what does it look like graphically? It's still going to do the same thing as before. It's going to calculate the distance under the max norm. And it's going to draw this square. So t v0 is going to be inside of this square. However, since we only update one state's value, so it should be either on this vertical line segment or on this lies above this this horizontal line segment. Because basically you just fix, for example, in this vertical line segment, you fix the vs1. You don't update s1's value. You just update s2's value. And suppose in the first iteration, you update s1's value, and then you basically the backup, sorry, not the backup value. The v1 is going to be lie on this horizontal line segment. And basically, you do the same thing. You calculate the distance, you draw the square, and you do the same thing again, and you can obtain this v2. It's actually very interesting to look at this diagram when we think about the requirement of asynchronous policy evaluation. Because in asynchronous policy evaluation, it requires that every state's value is going to be updated for infinite times. So in this case, if you look at the distance between v1 and v pi, and the distance between v2 and v pi, you find that these two distances are exactly the same. So when you do updates, the distance doesn't become smaller. And if you only update s2's value, you will the distance will never get smaller. So that means you really need to update the s1's value in order to get some improvement. Hey.
So you have these boxes, but the v2 is not inside the subsequent box that you drew for the second iteration.
Yeah, because for this box, it means that if you apply t Bellman operator to, for example, to v1, let's show it.
Oh, okay.
Yeah, yeah, because you don't do the full Bellman operator. Instead, you only update one state's value. So it can be outside of the box. Yeah. So for asynchronous policy iteration, it's similar as before, because as we mentioned, the policy value iteration is similar to policy evaluation. And now let's think about policy iteration, and now it will become a little bit more math, but don't worry, it's not too much. So for every iteration, what you're going to do is you do a full policy improvement, and then you do a full policy evaluation. very neat. So the way that you solve this policy evaluation problem is you can solve it by inverting this matrix. So basically solving a linear systems of equations. And how does it look like? How does policy iteration look like? Well, first I'm going to introduce a very interesting theorem. This is very useful. And basically it says that if there are two vectors and you apply the same Bellman operator on these two vectors, then the order of these two vectors doesn't change. And with this monotonicity theorem, we can show that v pi k actually increases monotonically. And this is a very short proof, but I don't have the time to talk about the proof today. So if you're interested, you can just check these proofs after the talk. So what does it look like? So first, let's think about v pi 1. As we mentioned before, the v pi k increases monotonically, and that means v pi 1 should be better or equal to this v pi 0. But v pi 1 should also be worse or equal to this v star, because for any policy pi, you can't, like, v star is the value for the optimal policy, and for any policy pi, it can't be better than the optimal policy.
What do you mean by vector 1 is greater than vector 2?
It means every element of the vector is greater or equal to vector 2. Yep. So now your v pi 1 should be inside of this box. And then you draw another box, which is because your v pi 2 is going to be like better than v pi 1. And you find v pi 2 here. And as long as you keep doing this kind of thing, finally it's going to converge to v star. And it can be shown that policy iteration actually converges to v star in finite number of iterations. So previously, we have talked about value iteration and policy iteration. There are actually two extreme cases where when you do value iteration, you do one-step policy evaluation and do one-step policy improvement. While you do policy iteration, you do infinite time steps of policy evaluation and one-step policy improvement. So modified policy iteration, or MPI, is a method between these two extreme cases. So in this algorithm, basically what you do is you do full policy improvement, and then you do partial policy evaluation on all states. And here it means that you do MK, so here it's MK, you do MK steps policy evaluation. And basically here it means that you update your policy for all states. Basically you find it's greedy policy for all states. And so for the convergence property, MPI actually has one more requirement. So in previous algorithms that we have mentioned, they just converge like under the discounted problem setting. But this MPI actually requires one more assumption, which says that the TV0 is going to be greater or equal to V0. And things that we can say about the behavior of this algorithm are two things. So here, so first, Vn is going to increase monotonically. And the second thing is this Vn is going to be better or equal to Tn multiplied with V0. So how to interpret these two conditions? This basically says what are the lower bounds of Vn. So because we have this kind of assumption that TV0 is better than V0, so we know that PV0 is on the upper right part of the V0. And for V1, because since we know that, Yeah, so for V1, since we know that V1 is going to be better than this TV0, so I basically draw the area of this TV0, and V1 just project to this place. Since we know that Vn is like monotonically increasing sequence, so V2 is going to be like in the upper right part of V1. And for V2, since we know that V1 is going to be better than this TV0, so I basically draw the area of this TV0, and V1 just project to this place. Since we know that Vn is like monotonically increasing sequence, so V2 is going to be like in the upper right part of V1. And for V1, since we know that Vn is going to be like And it's also going to be in the upper right part of t squared v0. So overall, it's going to lie inside of this intersection. So we find v2 here. And finally, because this t infinity v0 is going to converge to v star, and we know that this thing provides a lower bound for Vn, so we know that finally Vn will lies inside of this area. So this basically shows the lower bounds of Vn. And similarly, we can show the upper bound of Vn, but this is actually more complicated because we need to introduce a new operator. And we can show that this new operator is also a contraction mapping. And it's going to, and the v star is also the fixed point, only one fixed point of this operator. So what does this mean? This means if you apply this operator to a vector v, and you apply the MPI operator to a vector u, when v is greater or equal to u, then this one will be greater. This one will be better than this one. And how does it look like? Well, it means that you have such kind of upper bound initially, and you find your v1 should be inside of the, below this upper bound. And you have the second upper bound, and you find this v2 should also be inside of this area. And finally, because u is a contraction mapping and it's going to converge to v star, so finally this will provide us an upper bound for Vn. And we see that Vn is going to converge to v star because of this lower bound and upper bound. Okay, so I'm going to show you a diagram showing this kind of process. So first you find a lower bound and upper bound, you draw this kind of rectangle, and you find your next value estimate. And because of the monotonicity theorem, v2 is going to be better than v1. And it can't exceed v star because the monotonicity theorem, it says that you need to keep improving until you converges to v star. So it's going to be inside of this rectangle. And now for v2, you also have this new lower bound and a new upper bound. But as I mentioned before, v2 can't exceed v star, so it's going to be inside of this rectangle. And you find v2 here. Okay, so this is MPI. There are more methods, but I might not have time to cover today. So I will only talk about the conclusion of these methods. So I will only talk about methods and their conclusions. So asynchronous policy iteration, some people refer this method as the generalized policy iteration defined in Rich's book. So here I give it a quotation, which means that it's actually not generalized policy iteration. So what does it mean? In my definition, it means that you do partial policy improvement on SIK, so on some state. You randomly choose this state, and you do full policy evaluation. So this is just similar to MPI. Instead, in MPI, you do full policy improvement, and you do partial policy evaluation, and now you just reverse these two things. And the asynchronous policy iteration is also guaranteed to converge without the assumption that TV0 should be greater or equal to V0. Yep, but okay. So for generalized policy iteration, this is what we have seen in Rich's book. This is basically the algorithm. Yep. Yeah, this is basically the algorithm, and this actually we can think GPI as the most general version of the algorithm, and it includes all the previous algorithms that we have covered, but it only converges under this assumption. So here is something that you can check if you are interested. This is basically an animation of the GPI algorithm, but since I don't have time, I will not cover it. Okay, and finally, the generalized value iteration. It's very related to SORSA, and it's defined by Michael Littman and Chaba in 1996. So if you're interested, you can also check it. So the conclusion, we basically we introduced 9 different DP and ADP algorithms, and all these algorithms converged, while this number 7 and number 8 needs more assumption, like TV0 should be greater or equal to V0 to converge. And finally, analyzing the convergence property of dynamic programming is actually very useful because these convergence guarantees are actually very related to their simulation-based counterpart methods. Okay. Nico.
In the modified policy iteration animation, you had V0 and there's also like an M somewhere from the previous slide, which describes like how many times you do the Bellman operator.
Mm-hmm.
Can you kind of explain how the T-M fits into this animation?
So which part are you referring to? Vn or M? This is T pi 1 M1?
Yeah.
So it means that, so here it basically means you first define a greedy policy with respect to V0, which is denoted by pi 1, and to evaluate this policy by applying Bellman operator for policy pi 1 for M1 times.
Mm-hmm. Can you show that in the picture? Because you have like multiple iterations in this picture.
Oh yeah, so here the V1, basically V1 is equal to this thing.
Oh, okay.
I just write V1 instead of...
And so TV0 is only one application of the Bellman operator?
Yes.
Okay, thanks.
Rich?
So could you say some more about this extra condition at the top there? I thought if that's the original T, that it would always be true.
If it's the original T?
Yeah.
So when you initialize your V0, you can't make sure that this is true, right? Because V0 can be anything.
Oh, so that's basically saying that we're like an underestimate.
Yes,
As long as we're an underestimate B star, this will be true?
that's right. So for example, if think about a problem where all the rewards are positive, as long as you initialize V0 to be like it's 0 vector, then this kind of thing can be guaranteed. Hey, Matt?
So with that statement, if all of our rewards are negative, so we have a cost goal problem, we can't guarantee convergence with the modified policy iteration anymore, or?
That's true. If you don't have this this additional assumption, then you don't have the convergence guarantee.
Knowing something about the V star, right? If we initialize lower than V star, then we can guarantee, but.
That's right, yeah. That's unfortunate, but that's true. Wes?
Could you talk a bit more about what other conditions you need for generalized policy iteration?
And for generalized policy iteration, so it's very similar to modified policy iteration. Sorry. So you only need that your initial policy. So V pi 0 is your initial policy, while V0 is your initial value estimate. You only need that T pi 0 V0 is greater or equal to V0.
Also the same conditions.
Yeah, basically the same condition, because previously you have that T, and that's because you already get the optimal policy. And now, because you don't have the optimal policy, so you start from pi 0. Yep, Nico.
Do you know some intuition about when this will hold? Like you mentioned, with if you have 0 vector and you have positive rewards, then the other one will hold. Do you have a similar statement for this one?
It's a hard question. Actually, I don't have it. Actually, I don't know. Sorry, I can't answer your question. Yeah. But like, I think it's straightforward to see that GPI. So the problem happens in MPI instead of in GPI. So GPI basically has the same like requirement on the assumption as MPI. It's because you like MPI kind of thing. It doesn't guarantee that you can converge.
Right.
Yeah. And Wes?
Just a quick question for clarification. So when you mean that since these are vectors, you need every value to be?
That's right. Yep. More questions?
So when you bring function approximation in,
Yeah. That's something more interesting. I plan to talk about it, but today I don't have time. So
isn't it just true that all the bets are off function approximation? Oh, it's just an expression.
Do we have any results in the function approximation case?
So, hey, we can talk about it next time. So this is a linear function approximation where you have this kind of linear function. And very similar to tabular case, we have approximate dynamic programming and AADP and temporal difference learning. And besides the backup, like those contractions, we also have this projection, which is a non-expansion under the d mu norm. So these are like two cases, on policy and off policy. And so this is an example of the on policy approximate policy evaluation. And we can see that, so this example basically shows why TD fixed point should lie like inside of this region. Like we can actually derive that the TD fixed point should lie within this 1 over 1 minus gamma multiplied with this like min of the MSVE. So basically, yeah, I think this kind of way to analyze things is very useful. And we can also visualize off-policy approximated policy evaluation and show it actually converges. Sorry. Yeah, it's kind of zigzag, but it's going to diverge. Oh, this is the same thing as before. Yeah, pretty much similar. This is the off-policy approximation control, approximated control, which is related to Q-learning. And we see from this diagram that Q-learning is also going to diverge. This is just an example, but yeah, if we have time, we can talk about it in the future. And for a nonlinear function approximation, I can construct a function approximator in which it's going to diverge. So this is basically the function approximator, like this rectangle, and I can show that it's going to like keep moving from this position to this position, but never converges to the maybe this is the best position for V pi, and yeah.
Cool. I'm afraid to ask another simple question. You might have a whole other talk here. Thank you very much, Yi.
Thank you.